Hello and welcome to 1.8 of our unit. We are going to talk about the structure of the atom today, and I know you recognize this ancient historical figure, John Dalton, from Dalton's atomic theory, and I was just reminding you that a couple of sections ago we were talking about his discoveries and some of the things he came up with. We're going to push further on and talk about some more scientists who further developed the idea of the atom. J.J. Thomson is one of those, and you may have already studied about his plum pudding atom. He found that atoms, any kind of atom, will repel tiny negative particles. It will also emit little tiny negative particles, and later those tiny negative particles came to be called electrons. But he made some of these discoveries in the 1890s, and when he saw that little electrons, or he wouldn't have called them that, but these little negative particles were coming out of an atom, he thought that there must be some positive mass inside of the atom as well, because the atom itself was not charged, so it couldn't be made entirely of these little negative particles. So he proposed this, what he called a plum pudding atom, where electrons and protons, or negative charge and positive charges, sort of distributed evenly throughout this spherical cloud. And if you'd like to call it a chocolate chip cookie model or a blueberry muffin model, that might be a little easier to relate to than a plum pudding, because I'm not entirely sure what plum pudding is, or I haven't had it myself. So that was his model of the atom. The next scientist that came along, roughly early 1900s, was Rutherford. He came up with a gold foil experiment, and in this experiment, right here is a picture of it, he bombarded a gold foil with alpha particles. Alpha particles are really large, positively charged particles. And when he bombarded this gold foil with alpha particles, he was very surprised at the results. Most of those alpha particles went straight through, but some of them deflected. You can see some of them deflecting off and even reflected off of this gold foil, and that surprised him a great deal. He described the event as comparable to shooting a gun at a piece of paper and having the bullet bounce back. This reflected particle was very surprising to him. He thought that if we really had a plum pudding model and there were small positive charges throughout the atom, that this large alpha particle should just shoot straight through and you would not have it being deflected the way it is. So he was very confused about that, and it led him to propose a nuclear atom. That means an atom that has a dense nucleus, that has positive charge packed together in one central location. And that was a new idea for the world. So here we have our introduction to modern atomic structure. We have, based on these ideas and further research by a lot of scientists over the years, we've come to understand that the nucleus is not only composed of protons, or positive charge, but it's also composed of some other material as well, neutrons. It's also very small relative to the size of the overall atom right here. And this particular drawing is absolutely not to scale. And to give you a little bit of reference for that, if the nucleus of a hydrogen atom were enlarged to the size of a basketball, then the atom's ground state electron would be about 20 miles away. That would be the kind of scale that we're talking. So the nucleus actually is very small compared to the enormous amount of space inside the atom. Here we see protons are represented here by the yellow spheres, and protons We call them protons. You can think of protons are +1 charge. They're a positive charge. Neutrons, right here, are neutral. They're 0 charge. They just do not have an electric charge. Right there, those are the neutrons in orange. Mass is very important to understand as well. Protons and neutrons are large compared to the other atomic component that we'll talk about in a minute, the electron. So we say the relative mass is about 1 atomic mass unit, or AMU. Also, you may hear the word Dalton. That's equivalent of an atomic mass unit. So each of them is worth 1 atomic mass unit. Each proton is worth 1, and each neutron is worth 1. So here you try this little problem. Pause the video and see if you can get it right. If an atom has 9 protons and 10 neutrons, what is the mass of its nucleus? Here's the answer. 19 atomic mass units, or Daltons. Remember, each proton is worth 1 atomic mass unit, and each neutron is worth 1 atomic mass unit. We have pretty simple math. 9 plus 10 is 19, and that is the mass of that nucleus. Now, it's important to know another function of the proton. The number of protons that an atom has is very, very important because it tells us the identity of that atom. An element's atomic number equals the number of protons that it has. So, if you look on the periodic table, you see that fluorine has 9 protons. That makes it a fluorine atom. An atom that has 10 protons is neon. If an atom has 11 protons, it will be sodium. Magnesium always has 12. Aluminum always has 13, and so forth and so on. The atomic number is what we call the number of protons that an atom has, and that is what makes it the element that it is. So what about outside of the nucleus? Well, outside of the nucleus, we have electrons. You've probably heard of them. Electrons, you might even relate to electricity to help you remember the name electrons. They are a -1 electrical charge. Their mass is very easy. They are so tiny that we simply consider them to have 0 atomic mass units, simply because down here you can see it's 5.54 times 10 to the -4th relative mass, and that is so small that it doesn't matter in any of our calculations. So we just consider it to be 0. Here is a chart summarizing the subatomic particles. Their symbols. Oftentimes we write an electron as an E with a negative sign, and this just tells the charges and their relative mass. So here I wrote a few more ideas for demonstrating proficiency. There is a lot of content in here, and I just encourage you to do some interesting things for demonstrating proficiency that are maybe a little bit different than just rattling off and telling me all of the wonderful information and the facts that you know. You can try making models of some of the historical understandings of atoms, Thomson's, Rutherford's. You can make them a physical model or a diagram. You can create a model of the atom, either physically or a diagram of it indicating individual characteristics of the subatomic particles. You can develop tables or charts, games, flashcards, make a model or diagram of Rutherford's gold foil experiment. There are a lot of different things that you can do. I just would encourage you to try and be creative. Here are a few ideas for advanced proficiency. You're welcome to read through that on your own. And again, you're welcome to come up with some ideas because I know you are all so creative, and I would love to see what you have and some of the work that you're doing. So I'll see you in class.